but not vice versa. So if sigma algebra, then it is also algebra. But not all algebra are sigma algebra, so this does not hold. Okay, so be careful. And I think it is an exercise to prove that this is indeed an algebra. Okay, so now based on this algebra and sigma algebra, we define probability finally. Okay, so we define probability measure. Oh, probability measure. Or we simply say probability. As I said before, probability actually measures the size of an event. Okay, so that's why we call it probability measure. Okay, let's say omega f is a measurable space. Okay, that means omega is a set called sample space, and f is a collection of subsets of omega that satisfies the axioms of sigma algebra. Okay, let's say there is a function from this f, sigma algebra, to real numbers. Then this function PR is called a probability measure if it satisfies the following three conditions. Okay, 1. For all elements of f, P of A, PR of A is between 0 and 1. Okay, be careful. This PR is a function from this f to real numbers. So the elements of this f is a subset of omega. So this function takes a subset here. This is A is an element of f. That means A is a subset of omega. Okay? So it takes a value, it takes a subset and returns a value, real numbers, between 0 and 1. And second condition, PR of omega is 1. Okay? Remember, this omega must be in this, this sigma algebra. So sigma algebra contains omega, right? By the first axiom. So that means this function PR can take omega itself as an argument. And if it's the case, then its value is 1. So that's the second condition. Third condition. If A1, A2, and so on are elements of f such that AK intersection AL is empty set if K and L are different. So that means these subsets are mutually disjoint. Okay? And if that's the case, then the probability of the countable union of all these is expressed as the sum of the uh, the probability measure of each event. Okay, so this condition is important. If this does not hold, then this doesn't mean anything. Okay, so if these three conditions are satisfied for this function, then this function is called a probability measure. Okay, these are all definitions. But whether this definition is meaningful or not is another matter, and we will discuss that later. Okay, this is just a formal definition of probability, but maybe this is very different from what you have learned in high school. Okay. Uh, So let's see. And here's another definition. So let's say this omega and this f, this its pair, their pair is measurable space. And PR is a probability measure. Measure defined on this measurable space. Then we say this triple, omega, f, and PR, we call it a probability space. Okay. Well, we use this word space a lot in mathematics, which kind of implies it's basically a set with some structure. Okay, if a set with linear structure is there, then it's called linear space, like you might have learned in linear space, linear algebra. Okay, and also we can consider a set of functions, set of all functions which can be integrated. Then we can consider a functional space. And here we are considering sets with some function satisfying certain axioms for sigma algebra and probability measure. Then it's called probability space. Okay. So that's all for definition of probability. Probably in high school you might have learned that probability is something like relative frequency. Relative frequency. So you do some experiments and count the number of some events and divide by the total number of events. So, and that was interpreted as probability. Or it can be also considered interpreted as strength of belief. So belief. This may sound quite unscientific, but actually this is a very consistent way to look at probability. So it is actually used in Bayesian statistics. This is called frequentist approach. It's based on frequency, so frequentist view of probability. So there has been huge debate for hundreds of years regarding the interpretation of probability, but in mathematics, we don't care about those interpretations. Anything that satisfy the axioms can be considered as probability. Okay, so that's the beauty of mathematics. We don't do politics, we do math. Okay, actually, these things can be considered as a special interpretation of these probabilities. Okay, so it's an abstraction. So mathematical probability is an abstraction of all these concepts. Okay, so it kind of integrates all of these. But on the other hand, it loses meaning of probability, right? So it's just an empty concept which satisfy a certain set of axioms, and it does not give you, for example, what randomness is, what an error is. So we assume everything is already known in this sample space. In reality, we don't know what outcomes are there. We don't really know all possible outcomes. But in mathematics, we assume that we know all possible outcomes to begin with. That's an assumption. Then we can do some theory, rigorous theory of mathematics. So that is not actually directly related to the real world, but surprisingly enough, the theories developed in this way have many applications in real world. Since they are rigorous, when something goes wrong, we know what is wrong exactly. So we can, do some kind of approximations, or we can improvise some interpretation or some other tools based on experience. But in any case, this theory gives us the basis for further extension. Okay. Okay. You cannot hear my voice. Let's see. Can you hear me? I think nothing is wrong here. Okay. Okay. This recording will be deleted in after 40 days. 14 days, yes. So after that, you cannot watch this video on Canvas, but I will upload this to YouTube, so there you can watch in any time.